Very good morning, class. In the previous video, we have learnt about the levers. Lever was a simple machine which is used to change the direction of effort to lift the bodies, right? And we have seen that lever was one of three types: class 1 lever, class 2 lever, and class 3 lever. And I told you a trick to learn these classes of lever. If you know that, the trick was FRE. It means in the first class lever, fulcrum was in the middle and load and the effort are on the either side. In the second class lever, resistance or load was in the middle and fulcrum and the effort on the two end of the lever. And the last, the effort is in the middle in the third class of lever, and the fulcrum and the resistance or load are on the two end of the lever. Now today we will discuss some numerical problem from this chapter from the topic lever. So let's do the first numerical. So this is the first numerical problem. It says a crowbar of length 120 centimeter has its fulcrum situated at a distance of 20 centimeter from the load. Calculate the mechanical advantage of the crowbar. Okay, so let's see the question of these levers. They are very easy if you solve them by making the diagram. Okay, so let's make the diagram first. So we have crowbar of 120 centimeter length. This is complete 120 centimeter. It says that fulcrum situated at a distance of 20 centimeter from the load. Let's say load is working here at point A. This is load, right? And from the load at 20 centimeter, the fulcrum is situated. So let's say this is the point where the fulcrum is situated, and it is at 20 centimeter from the load. Now at this point, effort is acting, right? We are applying effort on this line, on this case. So the effort is acting on the other end of the beam or this crowbar, let's say at point B. In this question, we have to calculate the mechanical advantage. Now, if you know that the mechanical advantage of the lever is given by effort arm divided by load arm. What was the effort arm? Effort arm was the distance between the fulcrum and the effort, and the load arm was the distance between the fulcrum and the load. So in this case, you can see that the effort arm is nothing but it is FB, right? This is FB, and the load arm is nothing but it is FA. The distance between the load and fulcrum is given, there is 20 centimeters. So obviously the distance between fulcrum and effort, it will be 100 centimeter. Will be 100 centimeter, right? So the mechanical advantage is equals to 100 divided by 20, which is 5. So the answer of this question is 5. Mechanical advantage of this crowbar is 5. Always remember that mechanical advantage is the ratio of the forces, because the effort arm is also in meter or centimeter, and the load arm is also in the centimeter or meter. It means in the unit of length. So if we divide two quantities of same unit, we'll get a unit less quantity or dimension less quantity, and that is why mechanical advantage doesn't have any unit. So this is your first numerical. Let's see the second numerical. This is your question number second. It says A pair of scissors has its blade 15 centimeter long while its handles are 7.5 centimeter long. What is its mechanical advantage? See, this question similar to the first question, and scissors is also basically it's a class 1 lever where the fulcrum is in the middle and the effort and the load are on the other ends of the lever. So if we try to make the diagram, see my drawing is very bad, so it's a kind of scissor. So basically this will be the fulcrum here F, and these are the blades where the load is situated, right? So here the load is situated L, and from the handle we apply effort, right? So here it will be effort. Now according to the question, the blades is basically 15 centimeter long. This is 15 centimeter, and the handles is 7.5 centimeter long, right? So you know that how to calculate the mechanical advantage. Again, the mechanical advantage, that is MA, is nothing but it is equals to the ratio of effort arm to the load arm, right? So effort arm divided by load arm. Alright, effort arm is nothing but the length of the handle, and load arm is nothing but the length of the blades. It gives 7.5 centimeter upon 15 centimeter, which will give you 0.5 mechanical advantage. As you can see that in this case, the value of mechanical advantage is less than 1, right? And you know that the value of mechanical advantage in class 1 lever can be less than 1 or can be greater than 1. It depends upon the length of the effort arm and the load arm. Okay, so let's see the next numerical. So here's a question number 4, which says we have a diagram, we have a figure in which we have a beam AB and this is the fulcrum F. First, you have to tell the A part to which class of lever does it belong. Second, we have to calculate if the AB is 1 meter, it is given that AB is basically equals to 1 meter and AF is 0.4 meter. This. Then find its mechanical advantage, and third, calculate the value of E, that is effort, if the load is applied on the point A is 15 kgf, right? So the first part, to which class of lever does it belong? So in the starting of the video I told you a trick to learn the classes of lever, that was F, R, E. So in class 1 lever, F, that is fulcrum, is in the middle. In class 2 lever, R, resistance or load, right? We can name resistance, load as well. So in the class 2 lever, resistance or load is in the middle, and the class 3rd lever, effort is in the middle. Now in this case you can see that the fulcrum is in the middle. That means this belongs to the class 1 lever. Alright. Now second says that if AB is 1 meter and AF is 0.4 meter, find the mechanical advantage. So obviously total is 1 meter, AF is 0.4 meter, so obviously the FB will be 0.6 meter, right? Now mechanical advantage, the part B, the mechanical advantage is nothing equals to effort arm upon load arm. Effort arm divided by load arm. So effort arm is the distance between fulcrum and the effort, which is 0.6 meter, and the load arm is 0.4 meter. Will we give you 3 by 2 or 1.5. So the mechanical advantage of this lever is 1.5. In the last case, we have to calculate the amount of effort which has been applied at the point B. So we have mechanical advantage, we have load. Then from the formula of mechanical advantage, we can calculate the value of effort, right? So let's see. Okay, so C part, mechanical advantage. Mechanical advantage is given by load upon effort, right? So we have to calculate the effort. Effort equals to effort, or E equals to L upon MA. L, that is load, is given 15 kgf, and the mechanical advantage is 1.5. We have calculated MA before, so when you solve it, you will get the value of E as 10 kgf. That means by applying 10 kilogram of force, we can overcome the load of 15 kilogram force. So this is the, we can say, advantage of using lever. We have to overcome the load of 15 kgf, but by just applying the load of the effort of 10 kgf, we can overcome 15 kgf. Okay, so let's see the next numerical. This is the next question, question number 8. It says a lever of length 9 centimeter has its load arm 5 centimeter long and effort arm is 9 centimeter long. Now, see, by reading the question and by observing the figures given in the question, we can understand the class of lever. And to solve the numerical, it is very important to understand that what category of the lever is given, right? Now, see here that a lever of length 9 centimeter, that means the total length of the lever is basically 9 centimeter, right? So let's say this is 9 centimeter. Now it says has its load arm 5 centimeter long. It means, and what is load arm? Load arm is nothing but the distance between fulcrum and the load, and load arm is 5 centimeter, which that means it is less than the total length of the rod, and it lies somewhere between the rod because the load arm is 5 centimeter. So, and once more, that effort arm is 9 centimeter long. Effort arm is 9 centimeter long. In this situation can be only happen if the fulcrum is here and effort is here, right? And we know that the distance between effort, fulcrum and the effort is nothing but the effort arm, and it says the effort arm is 9 centimeter and the total length of the rod is itself is 9 centimeter. That means the effort will be lie on the other end of the rod and fulcrum will lie on this end of the rod, and the load is at 5 centimeter. So this is load which is at 5 centimeter from the fulcrum, right? So this is the diagram. What you have to calculate? Class of lever. The first part we have to tell what is the class of lever. So again, you know that from the trick FRE. R means resistance or load. If the load is in the middle, that means this is from the second class of lever. So the answer of the first part, that is A, is nothing but class 2 lever. Alright, this belongs to the class 2 lever. Second, diagram. You can see that we have already made the diagram here. And third, we have to calculate mechanical advantage, velocity ratio, if the efficiency is 100%. So previously you know that what is the relation between the mechanical advantage and the velocity ratio and the efficiency. Because to obviously solve this part, you must know the relation between the mechanical advantage, velocity ratio and the efficiency. So let's solve this part. Yeah, and the last part, the D part, we have to calculate the mechanical advantage and the velocity ratio if the efficiency is 50%. So let's first solve the part C. So in the part C, what we have to calculate? We have to calculate the mechanical advantage, the velocity ratio, if the efficiency is 100%, right? Okay. So you know that mechanical advantage can be obtained with the formula effort arm to the load arm. So in this case, the mechanical advantage will be equals to effort arm upon load arm. So effort arm is given in this question, it is 9 centimeter, and the load arm is given 5 centimeter. So this is your mechanical advantage, right? You can solve it or you can just leave it in the fraction form. When you solve it, you'll get 1.8, right? So this is your mechanical advantage. Now in this case, we have to also calculate the velocity ratio of this lever if the efficiency is 100%. Now what is the relation between the mechanical advantage, velocity ratio and the efficiency? So the mechanical advantage is equals to velocity ratio into efficiency percentage, right? So from here we can calculate the velocity ratio. So velocity ratio is equals to mechanical advantage upon efficiency percentage. So let's solve it. Okay, MA is 1.8. Alright, so VR is mechanical advantage, that is 1.8. Efficiency is 100%, right? So 100% means 100 upon 100 because it is in percentage, right? Which will give you 1.8. So the VR of this rod is 1.8, right? Mechanical advantage is 1.8 and the efficiency, because efficiency was 100%, and that is why velocity ratio of this beam is also 1.8. Okay, in the next question we have to calculate the mechanical advantage, velocity ratio if the efficiency of the bar is 50%. Now here's the concept. Always remember, the velocity ratio of any simple machine, it always remains constant. It does not change, right? If the efficiency is changing, it means that the value of mechanical advantage is changing. Mechanical advantage can be changed, but the velocity ratio of any simple machine remains constant, right? So in the last part, in that part D, we have to calculate the velocity ratio, mechanical advantage if the efficiency is 50%. Let's solve it. So in this part we have to calculate MAVR if efficiency is 50%. So as I told you that VR never changes. So VR in this case will be, again, it will be 1.8 as in the previous case. Now efficiency is 50%. So what was the formula of mechanical advantage? That was VR into efficiency percentage. So VR is 1.8 into efficiency is 50%. it is 50%, means 50 upon 100. That is 1 by 2. So when you solve it, you'll get 0.9. So this is your mechanical advantage. So I've solved some numerical of this exercise. Please try to solve another questions, and if you have got any doubt, you can ask me. We'll discuss some more numericals and the other concept in the next video. Thank you so much.